So the question that came in, you showed that graph and you showed that the pickup velocity is around 3,500 to 4,000 feet per minute for dilute phase. How does wave conveying physically pick up the material at a slower speed than that?
Great question. Yep. Let me, I'm a big illustration guy here, so let me open this back up again and show the translation, and I'll talk about it. So again, there's a breakout session that I'd love for everybody to join for wave conveying specifically at the Conair Summit. It's a video you can watch at any time, and it goes over this in detail. But long story short is dilute phase conveying, there's a very high P differential. This equation is Boyle's law. We take a dynamic understanding of that. We apply a rate to both sides of the equation to balance it. So instead of pressure and volume, we're using pressure and volumetric flow rate at the pickup point must equal pressure and volumetric flow rate at the receiver. In a dilute phase conveying system, we're at ambient pressure up at the pickup point, so that pretty much it's just with respect to the material handling line, the pickup point is at 0 inches of mercury, and at the receiver it's seeing, I don't know, call it 10 or 11 inches of mercury. So it's a pretty big delta P, delta pressure. And inversely, to balance the equation, we must see a delta V, and the pickup velocity is continuous, and it must be that 3,500 to 4,000 feet per minute, for example. So how does wave conveying work? What we do with wave conveying is we decrease the delta P. So we regulate a deep vacuum state from pickup point to receiver. And in order to balance the equation out, we also prevent the material from accelerating much at all. So we pick it up and we keep it moving very slow. And the result of this is we're able to achieve a much lower pickup velocity. And we do that by using a VFD and dropping the pump curve. So we're no longer up here. We're now down substantially lower, almost 20, 30, 40% lower at the pickup point, if not more. How we're still able to pick the material up, though, let me stop my screen here so I can make sure you guys can see me, because I have to use my hands. What we do is it's similar to if you choke off a vacuum cleaner. So imagine taking a shop vac or your home vacuum cleaner. At the end of the probe, take your hand and cover about 60-70% of that pickup point, or at the end of the vacuum cleaner. You'll start to experience a deep vacuum state. So you start to feel your skin pulling in and your hand kind of gets stuck to the end of it. Now take your hand, remove it, and put it back on. Remove it, put it back on. What you're doing there is you're breaking a deep vacuum state to atmospheric pressure. When you do that, you get a rush of ambient air. So you're breaking a deep vacuum to atmospheric pressure. That air is physically rushing into that pickup point. That's what our wave technology is doing, is we're getting that 3,500 to 4,000 feet per minute to pick the pellets up, but we don't have to do it continuously while still conveying all that material on the line. We're able to do it at much lower CFMs, which really results in much lower pickup velocity.
And then that velocity varies depending on the density of the material, the shape of the material, the size of the pellets, and that's why there are things like the ability to set recipes for different materials and different applications.
Absolutely. Yep. The bulk density and the shape of the pellet are the two main reasons there. I mean, heavier material requires a greater pickup velocity to pick it up, because it's like you're trying to pick up rocks, for example. But if you're trying to pick up feathers, which would be like your regrinds or your flakes or your fluffy material, it would require substantially less. That's why that window is a 500 feet per minute window, 3,500 to 4,000. That's general, but then it expands outside of that for both sides.